It's my pleasure to introduce our next star speaker today, Russell Luke. Russell is a professor for continuous optimization and variation analysis and chief financial officer for Faculty of Mathematics at University of Goettingen in Germany.
I managed to shake that second title. I'm no longer the chief financial
officer.
So I'm very happy about that, actually.
So congratulations that you skipped this.
Thank you, thank you.
Have more time now. Russell obtained his undergrad degree in applied mathematics at UC Berkeley, and he received his master's and PhD in applied mathematics as well from University of Washington under the supervision of Jim Burke, which was followed by Pacific Institute of Mathematical Sciences postdoctoral fellowship under the supervision of John Borwein and Adrian Lewis. Russell's research interests are fairly broad, mainly in variational analysis, optimization, and inverse problem. But in particular, Russell is a world-class expert in non-convex optimization problems and possible efficient algorithms to solve such problems, as we shall see today. And I think Russell is also going infeasible as well. So his work has application in many areas, mainly in image processing, inverse scattering, and computational quantum chemistry. And his recognized work has received funding from different places, the Natural Science Foundation, German Research Foundation, German Israeli Foundation, and Australian Research Council. Russell, the floor is yours.
Okay, thanks for the nice introduction, and thanks for the invitation to speak in this really nice forum. Right, this is kind of following up. I misspoke. It was actually Zhongxi Peng who gave a talk about the non-optimization, non-smooth, non-convex, and I'll add to that infeasibility, and I hope I'll explain that, what I mean by that, in the course of this. So I'm going to look at sort of two types of problems that are motivating some of the things that I've been looking into the theoretical side of things in the last several years. Systems of linear inequalities. So just solving AX is less than or equal to B, and also the Conan sphere problem. And this problem is an abstraction of the phase retrieval problem and source localization problem and other problems. But the abstraction is basically you want to find a point that's nearest in some sense to a cone and to spheres in the image of affine transformations. And I'll make that much more concrete in the slides below. So the system of linear inequalities, you can set this up as just as an intersection of these half spaces like CJ here, and the Conan sphere problem. It's a slightly more elaborate construction, but basically you've got these script FJs. These are affine mappings or linear mappings, and we then want to find points in these sets CJ, where under this affine mapping, we have an amplitude or a magnitude that's specified by this Bij. And then the cone part of the Conan sphere problem is added by this set C naught, which could include a support constraint or non-negativity constraint or sparsity or symmetry, whatever you might like. And then from those types of problems, there are model categories that, in my mind, kind of separate different algorithmic strategies. The very most primitive of all of these model categories is the feasibility model, where you just want to find some point that is in all of those sets, and you can extend that to these product space formulations where you take if you have M sets that you're trying to find the intersection of, you take your domain and you make M copies of it, and it's easy to find individual elements in each of these sets, and then you want to intersect this products, this product set of sets with D, which is the diagonal then of the product space. It's just another way of doing things, but I'll maybe explain a little bit if I have time how this is a kind of an implicit smoothing of this first model class. And then beyond that, there's smooth optimization, where instead of finding the intersections of the sets, you can just find a point that minimizes the distance to all the sets. This is very natural. And then beyond that, this is standard just constrained optimization. You know, whatever function you want to minimize, subject to x being in this omega. Omega is probably then the intersection of all of these sets Cj. And this is probably a point that I'm singing to the choir here in this audience, but I think it's kind of gets to the heart of where people focus their energy. And I work with physicists a lot. And physicists usually start down at the bottom of this sequence of implications. And they just start with some algorithm, some iterative procedure that they just do over and over until they see a point that they like and they stop, right? But we as optimizers, we like to start with an optimization problem. So let's start with a constrained optimization problem, minimize some function, subject to some constraint. I'm going to take that constraint. I'm going to hit it with an indicator function here. So it looks like an unconstrained, a non-smooth unconstrained optimization problem. And then as optimizers, we seek basically critical points, which is what this second thing here is. We want to find, and that's what gives us these optimality criteria, which is, this is just shorthand for an optimality criteria, necessary optimality criteria. That gives us something closer to an equation to solve, or a generalized equation here, since this is an inclusion here, that we can actually implement on a computer, because computers actually can't solve optimization problems. And then from there, from this system of inequalities that we get, or equalities, we then formulate an iterative procedure, which is just a fixed point mapping, right? And so then we change our problem from this generalized inclusion to one of finding a fixed point of some operator t, and then this operator t is going to be really our algorithm that we're applying. And then here's where we actually apply our algorithm and we generate our sequences. So the main question is actually, and Radu covered this, the reverse implication in his talk, but a lot of people don't actually. But you know, the issue is, you know, starting from the fixed point iteration, when can you follow these implications in the reverse direction? Okay, and when your function f is convex and this constraint set is convex, usually, and this is a linear space, usually everything is nice. You know, I mean, you can associate very easily fixed points of this operation with solutions to your optimization problem. But you know, the point is that you need this very, very nice regularity here. And then you can take things for granted and just start with your fixed point iteration. And the physicists then usually do just fine with just only focusing on that and not even worrying about what the optimization problem is behind the fixed point iteration. But it gets more interesting when the objective function is non-convex, or our constraint set is non-convex, or more recently, I've been getting interested in settings where the model space is not linear. So a non-Euclidean space. And then it's really not clear at all whether you can take these implications upwards. And it's not even clear what an optimality criterion is anymore, because we don't have linear structure. We can't, we can add, these are functions, right? But a subdifferential in a nonlinear space gets interesting. So that's what I'm mostly interested in. But let's look at, now I want to explain what a splitting algorithm is. So you've got a sequence generated by this fixed point iteration, or as Radu was showing, you could try to accelerate it one way or another. This is just one example of a type of acceleration. And this T mapping is it's a self-mapping on and a multi-valued self-mapping on some subset of our native space X, and it's a composition or average of resolvents and descent mappings. So resolvents one example of a resolvent here is if you have the notion of a descent, like a negative gradient, then the resolvent would be formulated this way, right? And that corresponds, if you do PDEs, that corresponds to taking an implicit step in your PDE solver, and the descent steps correspond to taking an explicit step. And we're going to assume throughout that this operator T has fixed points. Okay, that's when we get into these more wild settings, it becomes quite challenging to show that these possess fixed points. We'll take that as an assumption in the theorems that I'll present for you. So an example of an operator splitting method would be something where, you know, I've got this circle plus is sort of the generalization of addition, because if I'm on a nonlinear space, I won't always have addition, but I can take convex combinations of points in my nonlinear space. And that's what this O plus means. So I could take a convex combination of the point that my resolvent would send me to and staying put, and I compose that with maybe a descent mapping, again, the convex combination of going in that descent direction, going to the descent point, or staying put, right? So that would be an example. But let's get concrete here. So two concrete examples of the motivating problems that I showed you. The first one, systems of linear equations. And now here, M is less than N. So I have an underdetermined system, lots of solutions to this problem. And if you've seen some of my more recent talks, I've shown you this example. Now, you know, I like the most primitive model format, which is the feasibility. So I'm going to reformulate that as a feasibility problem. And that's just then finding the intersection of hyperplanes. And once you're there, then it's quite easy to motivate this idea of cyclic projections. You just project, you've got a closed form for the projections onto these hyperplanes. You can write that down and just code this up. Very easy to do. So you give this to your students. This is a first semester numerical analysis project, homework problem really, to code this. And there's a convergence theory for it, going back to von Neumann and Naransian, that when A is full rank, then this cyclic projections converges either finitely or linearly to some point in the intersection from any starting point. And then the students code this up. You give them an example, randomly generated matrix A, randomly generated Bs, say, and they get these results that look like this. They're iterates. Now I'm looking at the step size between successive iterates on this graph. And it goes down to about what that looks like, 10 to the minus 16, and then wiggles forever. And if you took a histogram on the size of these wiggles, that's what this plot on the right shows, is the histogram of the variance really of these points of where they are, and this is on a scale of 10 to the minus 16. So there's very little variation, but this is obviously, we all know this is just numerical error, but that's not in the theory here, right? And so we always say, okay, with errors, we add some epsilon. Each time we compute our exact cyclic projections operator and make some error, epsilon k. And then the theory is, well, if you've got vanishing errors, if the errors are summable, then you will still converge to something. But big motivation for me looking in these really abstract settings is that doesn't explain this. And I would be perfectly happy with this, and a lot of physicists are happy with this. You are converging to something, because this histogram on the right, that looks like a distribution. Now, that is a representation of the distribution to which these points are, now looking at these points here is actually random variables. So now I have something that I just need to change the way I'm looking at things to be able to understand the convergence of this. And that's one of the big motivations behind this. Second problem was the Conan sphere problem, inconsistent non-convex feasibility. So I got a Fresnel transform. It's a Fourier transform, a fancy Fourier transform with quadratic terms in it. A 128 by 128 image of a complex valued object. So I'm representing the complex plane by R2 here, and then and this is given to me. And then the other set here, C0, is depicted here. It's just saying that it's a support constraint. I just want actually it's support non-negativity, some real non-negative object that's supported in this yellow box. And the Fourier data that I'm collecting here is over on the left. So that's what these sets are. The BJs are individual pixels in this picture on the left. Okay, so and at each one of those pixels, it's just describing a
Russell, you've muted yourself.
Solving this problem. I don't care what other talks you've heard about phase retrieval, and they've all talked about, they've got like semi-definite relaxations and all this, and or phase lift or anything like that. Nothing can beat one of these three algorithms. You'll have to trust me on this. And all these are just iterated averages, iterated projections here, cyclic projections, TDR. This is the Douglas-Ratchford algorithm, or the relaxed Douglas-Ratchford algorithm here on the bottom. These are the algorithms that the physicists use. Nobody else on planet Earth except mathematicians uses these algorithms to solve these problems. So, and there's good reason, because these are the ones that work. So cyclic projections, if you plug that in for this problem and you plot the iterates, the distance between successive iterates, you get a plot like this that's showing this kind of linear convergence. And it wasn't until 2018 in this paper with Matt Tam and Tao Nguyen that we could prove that you should get linear convergence locally. And that's exactly what this graph is showing. And we can prove this for the geometry of the phase retrieval problem. But if you look on this graph on the right, what's happening here, we're looking at the feasibility gap. So we're looking at the distance between the constraint sets. So the distance between the point in this set and the point in this set. And that was 26, 25, I don't know what that is. That is not zero, and it's not converging to zero either. So this is numerically showing you that you have an inconsistent feasibility problem. Nevertheless, your fixed point operator is converging to some fixed point. That's fine. If you plug in Douglas-Ratchford to this, while I can tell you all about this, Douglas-Ratchford won't converge. It can't converge because it's an inconsistent feasibility problem. So, yeah, you know that basically what that says is that T, your fixed point operator, does not have fixed points. So it can't converge. And you plug it in, and indeed it doesn't. So you have to figure out a way to deal with this. And what physicists do mostly is they run 40 iterations of Douglas-Ratchford, stop it, and then run cyclic projections. And that seems to work pretty well for them. But motivated by that, I proposed a relaxation of the Douglas-Ratchford algorithm that's been sort of picked up subsequently, and it has the form that I showed you in the previous slide. And the relaxed Douglas-Ratchford method now does converge. We're looking at successive iterates here, and it reaches the gap that cyclic projections did. And if you look at these are not the same points, but they're very qualitatively, they're very similar. And in fact, the physicists were very happy with this image. This image, it's a very low resolution image of a coffee cup that Tim Zaldit's undergraduates produced in his X-ray physics lab for just a part of their course. So this was actually the answer, believe it or not. It's not a very good picture, but so the goals of this are when does, first of all, I mean, so there are lots of different questions you could ask. When do our formal optimality criterion that we formulate over here, does that correspond to the actual argmin of your function? That's the obvious question. The difference between minima and critical points, right? How do you calculate this? Not always easy, but subdifferential regularity, you can distribute the subdifferential through here, all of this. How do you calculate the inverse of this at 0? Right? Can you come up with formulas for that? How do you construct an operator, a fixed point operator, that finds you points that satisfy this generalized inequality? When do the fixed points of this operator correspond? Now, Douglas-Ratchford is one of these algorithms where the fixed points of the Douglas-Ratchford mapping actually don't correspond to these critical points, but you can get there by a simple projection. So that's what this tilde here means. But all I'm going to talk about in this talk is these last 3 points. When does the sequence defined by my fixed point mapping converge to a fixed point? How fast does it converge? And at iteration k, can I say something about how far away I am to the fixed points? So that's the whole goal of getting rate. So proximal splitting in nonlinear spaces, some preliminary. So I'm even though these problems are actually in Euclidean spaces, there is a reason why I want to look at nonlinear spaces, because actually the phase problem, you're on these circles. It's actually a problem on these spheres, really. So I'd like to look at spaces with positive curvature. And that would be the P uniformly convex metric spaces are really the right setting for doing this. And so what a P uniformly convex metric space is, it's a uniquely geodesic space that satisfies this inequality. And so you've got 3 points, x, y, and z, and you take a convex combination of x and y here, and you're comparing that with z here. And so this looks complicated, but for p equal to 2 and c equal to 2, this would then capture a Hilbert space, for instance. Now, in these settings, distance and projector are defined as you would expect. The distance is just the infimum. The distance to a set omega is the infimum over all y of this problem. So it's a solution to an optimization problem. And the distance function is the point at which that infimum is attained. It doesn't have to exist, so we need closure of these sets. And the projector would then just be, yeah, that's what that point is. And we have an inverse projector. This is just motivating a set valued mapping here, although the projector itself could be a set valued mapping. And I'll show you on the next slide that this is not so exotic. But if C is convex, then these projectors have lots of nice properties, still even in this P uniformly convex setting, that the projector is pointwise alpha firmly non-expansive. I'll show you the definition of that in a moment, at points in C, and the projector is a singleton. It's not the case that you can go conclude from single valuedness of the projector convexity in this setting, but you don't have to go to a very exotic example to show where all of this breaks down. If you just look at a sphere, so we got this funny S rho is a sphere centered at Z with radius rho. The projector onto this is multi-valued at the center of the circle, or at the center of the sphere. So this projector is neither pointwise alpha firmly non-expansive, nor is it everywhere a singleton. So you can't take these nice properties of projectors for granted. And more general than a projector are Prox mappings, and in P uniformly convex spaces, these are defined this way. It's the argmin over y in G is now the domain of our metric space of the function here with the distance to the point x. So we're trying to minimize this function, but also not go too far away from this point x. That's what the proximal mapping does. And so the projector is an example of this, where the function is the indicator function to the set, and in this case, the prox of the indicator function is just the projector onto that set. I don't need to tell you about set value mappings. Just keep in mind that the domain of a set value mapping is just the set of points where the mapping is non-empty valued. And it's but here I do have to be clear on what do I mean by the fixed points of a set value mapping. These are just the points such that when I apply t to that point, the image x is in the image of that. Okay, but that could be not very informative. But here's the first payoff to looking at things like non-expansiveness, or even almost non-expansiveness, which is kind of a generalization of continuity for set value mappings. So on a metric space, the mapping is said to be pointwise, almost non-expansive at some point in this D, on D. If there's some epsilon such that this inequality holds for all points in the image of x under T, for all points in the image of x not under T, for all x in D. So the point here is I'm keeping this x not fixed. I'm allowing x to vary around the set. So the pointwise refers to the fact that I'm fixing that point there. Okay, and this is basically one-sided Lipschitz continuity, and this sort of the set valued version of this. So you can look at this as calmness if you're familiar with that. And so the advantage of this property is that if your mapping is pointwise almost not expansive at some point, then it's single valued there, and you can see that directly from this inequality, because if it's not single valued at the point x naught, then I could choose another point in the image of that, and this would be greater than 0, even though this would be 0. So I violate that. Okay, so that's a good thing, and single valuedness at those points is what we want. But the key property for convergence of algorithms, fixed point algorithms, is alpha firm non-expansiveness, and this is a stronger property than just almost non-expansiveness. And I'll explain where the pointwise is coming in, where the almost is coming in, where the alpha comes in, and where the firm is coming in. Okay, so we're going to take, so we're focused on this point x naught on some set D, and we have to satisfy this inequality. Now, cover up the stuff with the phi t for a moment. Let's psi t for a moment. The first part of the inequality is just non-expansiveness, right? Everything's raised to the p power, so I've gotten rid of the pth root of 1 plus epsilon here. So it's non-expansiveness plus something a little bit more. And what this psi t is, I call it a transport discrepancy. It's defined by this equation 1 here. It's a very complicated thing, but what it's looking at is we got these points, we got x, we got a point x naught, and then we look at the points in the image of t at these points, and say this is tx. And what we're comparing here are these distances against then the diagonals. The diagonals are these negative distances, and all the other distances are just the lengths of the sides of this parallelogram. Okay, so this is the central inequality for actually getting convergence of fixed point iterations to a point. And this object psi of t I call the transport discrepancy. It's the central object in the convergence analysis. So on Euclidean spaces, for example, we looked at the Prox operator. The Prox of a convex function is alpha firmly non-expansive everywhere with alpha equal to 1/2. There's no violation, the epsilon is equal to 0, and it's not pointwise. So actually, this inequality holds also for all x naught in D. Projectors onto convex sets are alpha firmly non-expansive everywhere with alpha equal to 1/2, no violation, not pointwise. Projectors onto smooth manifolds, so not necessarily convex, smooth manifolds. These are almost alpha firmly non-expansive, so there's some violation. The epsilon is non-zero. On neighborhoods of the manifolds with violation, the violation can be made arbitrarily small as long as you're close enough to the manifold. So you can control the violation of alpha firm non-expansiveness by restricting yourself to neighborhoods close enough to the sets of interest. And then, another often appearing operator is the steepest descent step with some step length lambda. This is also almost alpha firmly non-expansive with violation arbitrarily small for small enough steps for a smooth function f. So these are just common examples of this. On P uniformly convex spaces, things get a little interesting. The Prox mapping of a convex function is only almost alpha firmly non-expansive. It's not alpha firmly non-expansive anymore, and it's only pointwise. So you lose this global property that you get on Euclidean spaces, and also you violate the property that you have in Euclidean spaces. The constant, however, the alpha constant and the violation, the epsilon, depend on the curvature constant of our P uniformly convex space. And that's where I get my results in that setting, because I can control that curvature constant by choosing a radius of my nonlinear space small enough. Projectors onto convex sets are actually pointwise alpha firmly non-expansive, no almost. But that's an interesting point here. A projector is just a Prox mapping of an indicator function. So the thing to notice here is that f is still convex here. For general convex functions, the Prox mapping is only almost alpha firmly non-expansive. But for projectors, things are nice. Okay, so that's onto convex sets. And the constant there is alpha equal to 1/2. For convex combinations, so this operator here is the nonlinear generalization of a steepest descent type step. You'll have to trust me on that. If f were the distance function, this would be the generalization of that to nonlinear spaces or to metric spaces. This with step length lambda is pointwise almost alpha firmly non-expansive. And again, the violation of alpha firm non-expansiveness depends on this constant b and also the curvature in the model space. So in a sense, we can kind of control that. So this is just an example. Now, there's a calculus of these things. When you compose pointwise alpha firmly non-expansive mappings, or you take convex combinations of them, you would like that property to be preserved in some sense. And so what we have in this general setting of P uniformly convex spaces is that when the fixed points of the mappings that we're composing and taking convex combinations of, when they have common fixed points, then there's a calculus. Convex combinations and compositions of these almost alpha firmly non-expansive mappings are also almost alpha firmly non-expansive, and you can calculate all of those, the constants involved in that. In cat zero spaces, these are P uniformly convex spaces with P equal to 2 and the curvature constant being equal to 2. Then you don't need to have the fixed points coincide. But anyway, this means that then you can apply all these ideas to the leading algorithms, which are just compositions and convex combinations of these kinds of operators. In convex settings, the pointwise alpha firm non-expansiveness at fixed points is all that's needed to prove convergence of the iterations. You don't need really anything else. That's just actually proving convergence at the distance. But to get convergence to a point, you might need something slightly stronger. The thing you need slightly stronger to get rates, anyhow, is metric regularity. I'm more a user of this for some of the fundamental work on this, you can take a look at these references. But what metric regularity is, so you've got a mapping from one metric space to another, G1 to G2. And this mapping T is metrically regular on some subsets of those domains, domain and image space, with gauge rho. And a gauge is just, all a gauge is a continuous function that is 0 at 0 and is monotone increasing in its argument. So whenever this inequality is satisfied, then you're metrically regular for all points x in the domain U and all points y in the image U2, but where the inverse of this mapping is just given by this. It's a set of points z such that the inverse at y is a set of points z that have y in its image. And so what you want to look at this as is Lipschitz. It's a type of generalized Lipschitz continuity of the inverse mapping, because the inverse of, if you apply T inverse to T of X, you get X back here, and you're applying T inverse to Y. If rho were just a constant, kappa, this would just be saying that the operator T inverse is pointwise Lipschitz continuous. So that's what metric regularity is in this more general setting. So the generic quantitative convergence result. Now this goes back in Euclidean setting. I developed this with Matt Tam and Tao Nguyen in 2018, and I've continued to develop this in more exotic spaces with Ariane Bedelima and my current PhD student Florian Lauster. Now remember, in the definition of almost alpha firm non-expansiveness, this transport discrepancy. Well, this comes in again, because we're going to require metric subregularity of a mapping built on that. So this surrogate mapping is, we're going to take, if you remember, this transport discrepancy had two arguments, x and y. And basically, we're going to integrate out the y argument. We're going to look at the infimum over all y in some set S, some subset of our domain G, some subset S, and look at the infimum of this transport discrepancy over all y there. And that's going to be a function now just of X, okay? So here's the basic result. So we're on a P uniformly convex space, GD, with metric D. T is a self-mapping on some subset of G, could be G itself. And the image is boundedly compact, okay? And we'll assume that T has fixed points. We assume that T is pointwise, almost alpha firmly non-expansive at fixed points. So this set S that I defined up here is indeed the set of fixed points of our operator T, with the same constant alpha at all of those points, and arbitrarily small violation on small enough neighborhoods of the fixed point set. So as long as I'm close enough to the fixed point set, I can make the violation as small as I want. If this surrogate mapping TS is metrically subregular for 0 on D with gauge rho, that just simplifies to this expression, this inequality. If this inequality is satisfied, then for any starting point close enough to the set of fixed points, the fixed point sequence converges in the metric D to some element in the fixed point set, with rate characterized by this gauge of metric subregularity rho. You get error bounds on this if the gauge is linear. So the rho is just a constant kappa, and the kappa is bounded by below and above by this. And the alpha, now this is the alpha in metric sub is the alpha in alpha firm non-expansiveness. Epsilon is the violation, it's the almost term. So as long as this kappa, which is the constant of metric subregularity, falls in this region, then for any starting point outside of the set of fixed points, the iteration converges to a point in the set of fixed points R linearly with rate given explicitly by this. And now you see all of the constants come in here for very explicit representation of the rate constant here. So that's the metric subregularity there, alpha firm non-expansiveness here, and the violation of alpha firm non-expansiveness here. And so here we can then get an upper bound on the distance of some iterate to the solution if we're Q-linearly convergent. So we get Q-linear convergence if the set of fixed points are isolated points. And the proof is actually, I'll do a proof sketch, is just basically you start with metric subregularity, this inequality 2, you start with that, and then you insert the assumption of alpha firm non-expansiveness by the defining inequality for that. That was in the definition. And that alone just gives you convergence to 0 of the distance of the iterates to fixed t. And then the hard work is involved in showing getting convergence to actual convergence to a point in fixed t. You need to show that this is a Cauchy sequence, and for that you're using properties of the gauge of metric subregularity as well as alpha firm non-expansiveness. So that's basically the proof of this generic result. Verifying alpha firm non-expansiveness is a master's thesis. I've given this out to one number of master's students who've been able to get this in a number of different settings. Metric subregularity is a PhD dissertation, but and it's actually the same thing as assuming the Kardika-Loyosevich inequality that Radu mentioned. Metric subregularity is a generalization of Kardika-Loyosevich. And in fact, if you want a quantitative convergence on the order of rho, metric subregularity is actually necessary. So you show, I was able to show with Mark Teboul and Tao Nguyen in a 2019 paper, and we later generalized this to metric space settings, that if all sequences converge with a certain rate to some point in a set, then those sequence of points is generated by a fixed point iteration, then the fixed point operator has to be metrically subregular with a rate generated by the observed rate of convergence. So back to this explains example 2 that I started with. We can now explain this yellow curve. We could explain the blue curve already with just in the Euclidean space setting. It took a few more years with Annalena Martens, a former PhD student, to get the relaxed Douglas-Ratchford algorithm, but we get linear convergence of that. And again, the point here is that this problem is inconsistent. And that's the innovation that was not possible until this paper, and building on the techniques that we developed in that paper. Very briefly, extending this to a stochastic setting. Again, so now here our native space is a Hilbert space. The T is going to be a self-mapping on a compact subset of a Hilbert space. And here what we're going to do is we're going to imagine that we have possibly an uncountable collection of mappings Ti. And these are self-mappings on this compact set D. Okay, so I got an index set, could be uncountable. And I'm going to generate a Markov operator from that. And the Markov operator has transition kernel given by this, which is just the probability, given some subset A and a point X, the probability that the image of X is in that set A. When I just take a random selection of these mappings. Now I've got a transport. My transport discrepancy is defined exactly in the same way here, but now it's a transport discrepancy with a randomly selected operator here. And so they're here now. I'm taking expectations, and I get a surrogate mapping in this in a space of measures that's the analog to, it's the direct analog to this guy, but now in a measure space setting. So this is a mapping from probability distributions on D to R plus. And so what we imagine here is just random function iterations. I'm going to randomly select one of these mappings, and I'll apply that to a random variable. Okay, and I start with some initial distribution. It could be a delta distribution. Okay, and I just generate these points, right? That is analogous to, I mean, that is exactly, you can describe that as a Markov chain, and it is a Markov chain, where the Markov operator is given with this kernel. And basically then what we're looking for is to find find an invariant measure of this Markov operator, given some starting distribution. And what we can say here again, if our randomly selected operators are almost alpha firmly non-expansive in expectation with some constant, and so they satisfy this inequality. This is just the measure, the stochastic analog to what I introduced earlier. Now we got expectations here. And if this surrogate mapping, which is really coming from this thing, is metrically subregular with respect to now the Wasserstein metric, 4,0 on the, this is the probability distributions with constant, now this is a linear, I'm doing this for the linear metric subregularity. So it satisfies this inequality here, and the kappa is given by this. Then for any initial distribution, the sequence converges R linearly, the sequence of measures now corresponding to those random variables that I'm observing, the sequence of measures converges R linearly to an invariant measure, and it depends on where we started. So that's what the U0 here says. With this rate, and the rate constant again takes exactly the same form that we had in the previous setting. And if this in the set of invariant measures is a single point, then we get Q-linear convergence. And that explains what's going on here. Because, and the difference here is, the conceptual difference is, instead of looking at a fixed fixed point mapping plus some error, what we imagine is that we randomly select projectors that are varying around these hyperplanes, and we select from these projectors, and when we take that viewpoint of the randomness that's coming into this, it's no longer an additive randomness, because you can actually show, if you have additive randomness, that there does not exist an invariant measure. But looking at it this way, so I'm computing an exact projection onto a randomly selected hyperplane, then you can show convergence to distributions. I can't tell you exactly what the distribution is, but I can tell you you will converge to an invariant distribution, and even Q-linearly. And this is the numerical demonstration of that. So there are lots of things to do in this. In P uniformly convex spaces, the Prox mappings were assumed to have common fixed points. We'd like to get rid of that assumption to develop a calculus for the inconsistent case. Also in P uniformly convex spaces, when does metric subregularity come for free? Some idea of like polyhedrality for nonlinear spaces would be very nice. Again, for P uniformly convex spaces, we want to now look at algorithms on manifolds or nonlinear spaces. And this is my target applications are angle resolved photon emission spectroscopy and femtosecond X-ray tomography. Also, in both of these settings, the Wasserstein spaces and the P uniformly convex spaces. So actually, I was assuming in the most general settings, a single value mapping. We actually need to deal with some details to deal with set value mappings there. Again, in both of these settings, when does the set of fixed points correspond to critical points? How do you characterize critical points? That's an open issue. That's this. How do you characterize critical points in both of these spaces? In Wasserstein spaces, this opens the door to a whole bunch of new algorithms for MCMC that you can do, and I'd like to explore that. And then also obvious applications to randomized algorithms for large-scale distributed optimization. Again, it's my application to femtosecond X-ray tomography and machine learning. So with that, I'll show you some references, and thank you for your attention. A few papers are still, this one's in revision. This one is also in revision. It's taking a long time to get this one out. This is the hard paper random function iterations for stochastic fixed point problems. This one has appeared, but this is the easy case, consistent stochastic feasibility. And then these other papers, I'll let you look at those. So, sorry, thanks. I've gone a little bit over.
Thank you so much, Russell, for the very interesting talk. Are there any questions or comments to Russell? Questions or comments? So, Russell,
I have a question. Okay.
Oh, go ahead. I can wait until go ahead.
Okay. So, Russell, thank you for a nice talk.
Yep.
So, you just mentioned different communities working on let's say solving the map or applying the map algorithm for non-convex problems. And you said that okay, the only available candidates from a point of view, okay, are the ones using projections, not only map. So they are and they are lambda.
Right, these guys.
Okay.
Yeah, these guys.
Okay. So,
I mean, or if you think you have a good algorithm, you have to beat one of these.
okay. But then what I know is, I mean, there is a group of people, I mean, these are mathematicians, but coming from a different community. So people working in harmonic analysis,
Right.
okay, where they use an algorithm called Griffin-Lim algorithm. And what they do alternative projections and then combine it with a nested of inertial step.
Okay.
I mean, yeah.
Okay, so
and they claim that the algorithm gives fantastic results.
yeah, okay.
So much better than without this extrapolation.
I'm not addressing accelerations here. You know, these are parameter-free methods, and so you're right about that. Yeah, I mean, but I guess in my mind, I don't look at an acceleration of one of these as really different. You're building on these, that's fine. But what I do want to poo-poo, and I don't apologize for this, is phase lift. That's a ridiculous idea where you take the square of the number of variables, and a lot of people spend a lot of effort on that, and I just think that's just a waste. It's been a waste of people's time. And then this other Goettingen flow, all Goettingen flow is gradient descent in the image space, and that's worthless too. So really, I mean, and they publish a lot of papers, again, in the harmonic analysis community. They publish a lot of papers. It's kind of their own little echo chamber. And the reason for not comparing to these methods is they say, oh, these methods, the theory is not well understood. Well, the theory is very well understood. So.
I mean, okay, let's say the Griffin-Lim supporters, of course, they don't have convergence proofs. They just apply the algorithm and they claim to obtain very good results. And but this is quite strange. I mean, they combine let's say a non-convex algorithm. I mean, they apply this algorithm to non-convex problems with a rule which is known to work in the convex case. But they are actually very happy with what they get.
We've done that for a tychography problem, which is a slightly more difficult version of this. We applied a Nesterov acceleration to that, and that also made marginal improvements. So there's something to do there, because understanding how you choose the acceleration constant for the non-convex problems, that should definitely be something on the to-do list. I think that's interesting. That would be very
thank you.
Good to look at. Yeah.
Thank you, Radu and Russell. Any more questions or comments to Russell? Okay, so Russell, I have two questions. So when you mentioned relaxed Douglas-Ratchford, could you please go back to that slide?
So
you were comparing it to Douglas-Ratchford when they perform for inconsistent problems. I think it was earlier than
this one.
Previous one, like before. I just don't remember the number of this one.
Let's see. Well, okay, this was.
It was for problem one, if I remember correctly, and.
Well, I didn't do Douglas-Ratchford for the linear systems of equations. I only did cyclic projections for that.
No, what I'm saying is that you actually compared Douglas-Ratchford to relax it. Yes, here. Yeah. This slide. Yes.
Right. So this one.
Yes, I'm looking at the one where you define the operator.
Okay, where I define the operator here.
Yes, here. So when you look at this and you like,
Oops, I might have made a mistake. No, that's right.
no, I think it's right because I looked at the paper as well.
Okay.
But my question is, if you're applying this to inconsistent problem and you compare it to Douglas-Ratchford, you're talking about inconsistent, and I think earlier you commented on inconsistent, but you were staying convex, correct?
Well, okay, so this is both inconsistent and non-convex.
Okay, and if you're doing it for inconsistent and convex,
Yeah, sure, because their local is global and then the shadows converge. That's not a problem. But in non-convex, Douglas-Ratchford's gonna try to send you in the direction of the gap
yes,
between the sets, and eventually you're going to get out of the domain of attraction of the shadow, and you're going to get pulled somewhere else. So yeah, looking at the shadows is what you would want to do for looking at the relaxed Douglas-Ratchford algorithm.
exactly. I mean, in the consistent case, in the convex case, even if we are inconsistent, the Douglas-Ratchford itself, the operator itself, would not do any well because it won't have a fixed point, but the shadows will give us a best approximation solution.
Sure.
So
yeah.
have you tried it in the setting of the non-convex as well? Like did the shadow do any well there?
Well, that's exactly what this is. This result, this DR, you seeing it. That's
Okay.
what it does.
Oh, okay.
Yeah. So
Okay.
you see the orange line, it's going up and down. What it's doing is it's approaching the gap, and then it's moving away, and then it just sort of stays away in this sort of nebular
I see.
orbit somewhere. So that's what you're seeing. Yeah. The shadows don't do anything.
Okay. And on page 34, I have a quick question.
Page 34.
Yeah.
Oh, let's see.
Yeah, it's at the bottom here. I can see the numbering at the bottom. Yes, well, 34, yes. When you say like when the fixed points coincide, do you mean that they are identical, or you mean that they intersect? They have
when they have, yeah. So let me see, what did I do with my pen? So you've got T1 composed with T2. You can say something about, or let me see. You got T1 intersect T2 is non-empty.
Like the fixed points, you mean like the fixed points intersect, but not necessarily like the fixed points that intersect. I see.
Right.
But not necessarily, like they are not necessarily equal, of course. Like we don't need the fixed points to be the same.
Well, certainly at points where these sets intersect, then yeah, they'll be the same, right? And so you get these. I should put pointwise here, because where the calculus holds is at those points where the fixed points are the same.
Okay.
And that's a huge limitation to this stage of the theory. We need to get to the inconsistent part of that. But that's in these really positively curved metric spaces in cat zero spaces, so Hilbert spaces or Hadamard spaces. Then you're fine. You don't need this requirement. Yeah.
Thank you.
Yeah.
So Rasime, okay, I have a follow-up question. I mean, so going back to the regularized or perturbed Douglas-Ratchford algorithm, so dr lambda.
Yeah.
So what I guess is that you can expect their strong convergence because of this construction, which is very much similar to Halpern or Tikhonov type algorithms. Is this correct? I mean, not for TDR, so this should only converge only
TDR lambda. Well, what TDR lambda is? So TDR is applied to minimize the indicator of C0 plus the indicator of C1. TDR lambda, you're changing the optimization problem, and what you're solving is minimize the square distance of X to C0 over X in C1. and you apply Douglas-Ratchford to that.
Yeah.
With a I've got this lambda, some lambda parameter here. I'm not sure how the lambda comes. There's a formula, I think it's like lambda over 1 minus lambda or something. So with some 4 factor here.
Okay.
And if you apply Douglas-Ratchford to that proximal instead of projectors, just doing that, then you get exactly this.
Yeah, but my guess is correct. Since what you have a kind of strong convexity induced there, in the objective, and this might give you strong convergence.
Yeah, I think that's a good way to think about it. Even though, I guess when I first was studying this, it seemed counterintuitive to me that you would leave the constraint set, the non-convex constraint set, as still a constraint set, and you would relax the convex set, because C naught in this example is the convex set. In this example, this is a convex set. And that's the one you relax with the distance function, which initially I thought that was counterintuitive, but I guess for you that seems the natural choice. Why would you do distance squared to C naught instead of distance squared to the non-convex function? I mean.
But let me be more precise. So I would talk about the Hilbert case and the convex case. Yeah, I mean, convex and Hilbert. Yeah. Then this scheme here gives strong convergence. Yeah.
For the shadows, I think rather not the governing. For the shadows one, like.
Oh, probably for the shadow.
Yeah.
Yeah.
It's not necessarily. It's not known. Like I don't think that the governing is necessarily convergent strongly in this case.
I'm not sure. I mean, for the shadow, you have this even for the R, I guess.
Yes. For the R, it's like the shadows definitely converge strongly.
No, but I'm talking about this perturbed DDR, and I mean, see, this is very similar to, let's say, a Halpern algorithm, which converges strongly. And also, there is a class of such methods, where by using this type of perturbation, one can improve the type of convergence from weak to strong.
Yeah. I mean, so I don't know if this kind of fits into a Ogazo type of.
Ogazo is different, but I mean, it's the same direction. Let's say. I mean, there is. So I guess Fran Aragon has a paper on this DR lambda algorithm, and he and Sean Wang as well, I guess, and I'm sure they proved strong convergence.
Okay. Yeah, I mean, Min Dao and Hong Fan, I think, and one other, maybe just the two of them. They looked at a whole class of the relaxed Douglas-Ratchford for a whole range of parameter values, and so this would just be one of those. And they have lots of parameters in there as well, so capture all kinds of things. And also, I mean, TK Peng and Goettingen Li have also looked at that, and they got some strong convergence results with the assumption that the sets have non-empty intersection, and also using Kodika-Loyolzevich.
So any more questions or comments to Russell? Or Radu, we still have time, if you have time, Radu?
Yeah, I have time.
Sure.
Okay, any more questions to our speakers today? Well, if not, let's thank our speakers again. Thank you so much, Radu and Russell, for the wonderful session. And